Okay.
So now if we go back into,
So now I don't care. Well, I can,
yeah, if we open the
I
PowerPoint.
can just watch this.
But if we go to the back to the PowerPoint now and open the PowerPoint up, and then, yeah, yeah, okay, cool. Yeah.
All right, let's get started, everyone. All right. Oh, that's really loud. Our two speakers today are both students of Professor Palawa. Our first speaker is Christopher Barth. Chris completed his undergraduate degree in ECE at the University of Illinois, and he is currently working towards a master's degree under Professor Palawa. His research is focused on algorithms and hardware for PV maximum power point tracking. Prior to beginning coursework in engineering, Chris completed an associate's degree in applied technology, and when he's not involved in academic pursuits, he enjoys applying his technical aptitude to various hands-on projects, including automotive and small engine repair.
Well, thanks for the opportunity to stand in a tunnel with you all and talk about dithering digital ripple correlation control with digitally assisted window sensing for solar photovoltaic maximum power point tracking. It's a very appropriate title for the paper, but should probably be shortened for the presentation. But basically, this is a quick overview of what I'm going to talk about. Just a very, very quick review of what PV maximum power point tracking is, and then more specifically how PWM resolution affects our maximum power point tracking capability. I'm going to review the dithering digital ripple correlation control, which I've talked about previously and is based on Professor Krein's work. Then I'm going to talk about how we use a windowed ADC measurement technique. And then finally, I'll show how we apply this measurement technique to the maximum power point tracking algorithm and achieve some impressive results. So first of all, maximum power point tracking. As we know, the power, the IV curve of a photovoltaic panel is nonlinear. And so what that does is it gives us a maximum power point or a value of current and voltage at which the panel power is maximized. And clearly, if we change our panel current in either direction of this IMPP, our power generated through the panel drops off. So in order to operate at this panel maximum power point, we need fairly good control over the converter, which in a switching power converter, our control resolution is determined by our duty ratio resolution. And so, which is basically just the resolution with which we can adjust the duty ratio of the converter. Now, this in turn is limited by the clock frequency of our microcontroller in applications where the buck converter is being controlled by a microcontroller. And so what we come up with is this relationship whereby if we're switching at a high speed or if the microcontroller is running at a low speed, we have a fairly coarse control resolution on our converter. And what this will cause us to do is to jump back and forth around the maximum power point without being able to nicely focus in on and operate at the maximum power point. As you know, perturb and observe is one tool to track the maximum power point, one algorithm. And basically in this approach, the duty ratio is simply adjusted and the change in power is evaluated with each adjustment. And basically depending upon the change in power that resulted from the previous adjustment, the next adjustment will either progress in the same direction or reverse directions. I lost it. Okay. So what can we do about this coarse duty ratio resolution? Well, one approach that's commonly used is dithering. And what dithering allows us to do is to operate between the extreme points at which our native PWM duty ratio resolutions would place us. So here we're operating at a high duty. Our panel voltage falls, our panel current rises. And then when we switch back to a low duty, the panel voltage falls and the panel voltage rises and the current falls. But if we quickly dither back and forth between these two duty ratios, we can see that the current and voltage never reach the native steady state values, but instead we're able to adjust this ripple in between the limits that would be imposed by a coarse duty ratio resolution. Now, this deals with our control resolution problem, but it also causes other problems. And that is basically we end up trading off control resolution for tracking speed. And so what happens is in a typical power converter, we need to wait several switching cycles after a change in duty ratio before we can reevaluate our maximum power point tracking algorithm. When we're dithering, we need to wait several dithering cycles, depending on the converter slew rate, for the converter to arrive at a new steady state ripple. And this is basically a filtered panel voltage, which is what our actual control will be based upon. And we can adjust this time constant of this filter so that this filter exactly tracks the average magnitude of the panel voltage. However, there as well, as we decrease the time constant of the filter, we're allowing the filter to ripple more during these dithering intervals. And again, that's decreasing our tracking effectiveness. So with these constraints, we have this clear trade-off between resolution and tracking speed. But then you could ask the question, is it really necessary to wait for the converter to reach steady state? Well, for P&O, perturb and observe, it is. But for dithering ripple correlation control, I'm going to show you that we can immediately reevaluate the maximum power point tracking algorithm after every dithering cycle. So DDRCC, or the dithering digital ripple correlation control algorithm, is based on Professor Krein's work on ripple correlation control and some of Jonathan Kimball's work as well. And what it does is it just takes into consideration this ripple that we have in panel voltage and current. Now, if we correlate these two plots, we can see that as we dither, this change in current causes us to transverse the PI curve of the panel. And so if we sample measurements carefully at the right interval, we can actually determine where we are on this plot. And because this happens every dithering cycle, we can immediately determine where we are on the plot without waiting for the converter to come to a steady state equilibrium. So basically, we'll know where we are at each interval as the converter moves to its new equilibrium. So exactly how do we accomplish this control technique? Well, it's based on the derivative of power with respect to current at the maximum power point. Because it's a peak there, we have a derivative of 0. Now we accomplish the change in voltage and current with respect to time. So obviously power also changes with respect to time. So we break this fraction up into the product of two fractions, and these are both derivatives with respect to time. And then we can see that depending upon the sign of this product, so if we're over here and we increase current in time and power increases in time, this product is positive, and that indicates that we're at some I less than IMPP. Now, if we're over here and we increase current, dIdt is positive, dPdt is negative, and that tells us that we're at some I higher than the maximum power point I. So by performing an integral control on the product of these ratios and applying a gain, we can converge to the average duty ratio at which we want to run our converter. So we're not going to be performing integrals in an 8 or 16-bit microcontroller that we're going to use for maximum power point tracking. So we evaluate that integral in a discrete form, and what this basically tells us is that by iteratively taking the sign of the difference in power between p equals 0 and t equals 0 and t equals RDTD, if we evaluate this iteratively, we'll converge to the optimal duty ratio, or the DMPP. So now we've addressed the issue of control resolution and tracking speed. And it sounds great, but when we actually go to implement, there are some challenges. And specifically, I'll draw your attention to this delta I here, or the delta V here. Now this dithered voltage and current ripple is sitting on top of a much larger signal. So if we're going to set up our microcontroller and our analog inputs to our microcontroller ADC to measure this signal, we're going to have to scale our for instance, 0 to 5 amp input signal into the microcontroller ADC. So just to reiterate that, basically as the panel current changes from 0 to the maximum power of the panel, that all has to fit into the 0 to 2.5 range of the ADC. So our input amplifiers will scale this all into that 2.5 volts. Now that sounds nice until you realize what actually happens in a low-cost microcontroller when you're sampling. What this is this is a high precision sweep of test current, and these are the values, these are the readings that were yielded by an Agilent multimeter and the unwindowed MSP430 ADC. And what you have here is just random noise. There's a couple sources of this. There's the microcontroller clock itself, which couples into the ADC and can produce ripple. And there's also obviously the EMI of the converter itself. Now this test was actually done with the converter not running, so this is mostly the microcontroller itself with the addition of any noise that might be coupled in through the amplification circuit. And what we see here is that we have a 25 milliamp noise fluctuation, and this is really going to make it impossible to measure the small delta I that we need to for maximum power point tracking using DDR-CC. And we have a similar problem with voltage, although it's not quite as significant because of the way the voltage is measured as opposed to current. So what we're going to do with this signal is we're going to take basically a smaller sweep of this full current range at a time. And so what we're going to do is we're going to window our full current range into the microcontroller ADC. So basically what I mean by windowing is we're going to take this basically almost negligible signal from the sense resistor that's measuring current at the input of the power converter, and we're going to amplify it up till the ripple magnitude is reasonable, till the ripple magnitude fills a measurable, significant percentage of our ADC range. And then, because as you can see, this will put us up near 80 volts, way outside the range of our 2.5 volt microcontroller, we're going to shift that signal down into the range of 0 to 2.5 volts. And so this obviously, because our op amps are running at 5 volts, this is not performed sequentially. Instead, we have a circuit that performs this functionality where we have the V-sense that's multiplied by some gain. From that, subtracted a V bias multiplied by some gain, and that gives us this amplified and scaled signal. Shivan, would you mind? And then, as I'm sure you picked up on, basically this window will be moved as the current through the controller changes, or through the converter changes. So as the sun comes out and the panel is able to produce more power, the current will rise and our window will rise up with it, so that we achieve this nice ratio of microcontroller ADC input range to the ripple to the ripple signal into the ADC. Now, what does this allow us to do theoretically? What we're basically doing is we're taking the full range of the ADC and we're focusing it on these little intervals. So here I have this very hypothetical 4-bit ADC. That's going to give us 16 discrete values we can divide our current signal into. But if we compress these into a small fraction of the full range that we need to measure, we basically scale our ideal resolution by the number of windows we divide into. Now, how do we accomplish this in hardware? Well, this is our microcontroller. This is a representation of our amplification and windowing circuit. And we measure panel voltage just using a voltage divider, and panel current by measuring the voltage across the sense resistor. And then, again, this is the conceptual depiction of what we're going to be doing. We accomplish this using two different circuits. We actually window both the current and the voltage. This is the voltage circuit. This is the current circuit. Because of the ranges that the voltage operates over, the voltage operates from some 50% of open circuit voltage to 100% of open circuit voltage. Basically, we don't need to go down to 0. So we bias this a little bit differently than we bias the current, which goes from 0 to full, the full short circuit current of the panel. But basically, these bias voltages are filtered voltages from the PWM, an extra PWM channel in the microcontroller. And what this setup does is it allows us to amplify this small signal range to fill the full range of the microcontroller ADC, and then we shift this full range up and down as the current changes. Now, I'd like to point out, much to hopefully Andrew's pacification or delight, that we're able to use this technique because of the application. So, as I showed you before, we're trying to measure that small voltage and current ripple. We can accept some loss of accuracy in the DC level of that ripple. What we really need is high accuracy in the ripple measurement. So basically what I'm saying is that we do lose some absolute DC accuracy in the measurement because of nonlinearities and non-idealities in this circuit. Also, the circuit obviously changed between converters and that type of thing. But in exchange for giving up a little bit of DC accuracy, we're able to achieve high precision measurements of the ripple signal. So what's the end result? This is the same test with the current window set to 1/32 of the full, roughly 1/32 of the full current range. And by windowing the current signal in that way, we're able to make the minimize the damage, if you will. We're able to minimize the relative noise that comes into the microcontroller ADC. And then we just append these measurements end to end, and as the current into the converter changes, this gives us some decent resolution over the whole 0 to short circuit current range of the panel. So this looks pretty. Can we evaluate this a little bit more quantitatively? This is not a discussion on signal assessment, noise assessment. All I'm doing is going to quickly show you that yes, in fact, this approach does help us. Basically, there's a characteristic for ADCs called noise-free code resolution. This is different than the effective number of bits. The effective number of bits, or the ENOB that you frequently hear about in ADC specs, that's an AC specification. So the noise-free code resolution is a DC specification. And because we're taking these samples at certain points in the signal, we really are interested in a noise, in a DC measurement. So theoretically, if we window, or if we don't window, if we measure the whole current signal with one setting of the ADC, we could achieve 4.9 milliamps of measurement resolution for a 5 amp range. But in reality, this value is, this resolution is decreased significantly by the distribution of noise that we have at the input of the ADC. And if you work through this, basically, based on this sample data, you could say that roughly we're going to have about 31 milliamps of resolution using a full range setup. Now, if we window, what we're actually doing is we're taking this noise, this full noise here that's basically from the circuit and from the microcontroller itself, and we're compressing it into a small region around the measurement point. So obviously we're not getting rid of it, and in fact we may be coupling in slightly more noise because we have a little bit more amplification. But because it's in this small constrained range, we're able to deal with it because, like I showed you in that plot, it's less significant in the total measurement spectrum. So if we apply the same analysis, we get about an 8x improvement in our noise-free resolution, and we come out with an effective number of bits of 10.3, and this is a 10-bit ADC. So this is basically just what you'd expect when you purchase the ADC. So what we effectively did was we took out the consequences of that noise. And again, this is because we're less interested in the DC component of our measurement, and we want to obtain a high precision measurement of the AC ripple. So this is pretty, but did it actually work for our maximum power point tracking? The answer is yes. And by adding this circuit to our converter, we're able to apply DDRCC in a scalable way. Previously, we had demonstrated at low voltage and low current where we could simply scale the entire 0 to I short circuit current into the ADC, and we could just simply scale the voltage into the ADC. Again, as the panel power rises, as the DC magnitude of the voltage and current increases, that approach just was not effective for the reasons I showed you before. But we applied this circuit, and we're able to get quick convergence. The 90.3% convergence or tracking efficiency that we were able to get for DDRCC using this implementation stands in contrast to the 97.4 that we would get for undithered perturb and observe. And we're able to accomplish this maximum power point tracking technique much faster than an undithered, at about the same rate as undithered perturb and observe, possibly a little bit faster, but we're able to track the maximum power point much faster than we would be able to if we used a dithered perturb and observe. So with that, basically what did we accomplish? We accomplished high PWM resolution using an 8 megahertz microcontroller, and we were able to accomplish great maximum power point tracking with this dithered with this dithered approach. The windowed measurement allowed us to scale the theoretical, basically, if you will, theoretical implementation of DDRCC that we were able to demonstrate before, where we just had a very small panel. This shows that using a windowed measurement technique, we're able to scale that up to a full standard panel power. The windowed measurements can also be applied to other, for instance, perturb and observe maximum power point tracking techniques, and it will be easier. So this windowed measurement technique may be even more helpful in less aggressive MPP tracking techniques. And again, like I showed you, the hardware requirements are pretty minimal because we already need to multiply or amplify the current sense resistor voltage. So we're already going to have an op amp on the converter, and they often come in quad packs, so we use a couple more of them, and we're able to window and measure that signal with fairly high precision. So thank you for your time. I just wonder if there's any questions at this point. Srikant.
Maybe I did not get you before, but when you talked about synthesizing a certain duty ratio, you talked about a high and a low initial part of the synthesis. So how are these decided? What do you mean by high and what is meant by low? How to define the high and the low duty ratio?
These are adjacent native duty ratios.
Okay.
So this is, 1/32 and 2/32 in this instance. So those are the closest we can get using the native PWM hardware.
Okay. So, but you effectively move out of the curve a little bit, and then this both ways you would move out of the nominal optimal value, right? When you change one high duty ratio would correspond to a point on the one side, the other duty ratio would, because on the peak curve, there could be a problem. Let's say the optimal point is at C, and then when you move to the point, when you're closer to the optimal point, on the right side it could be more damaging than on the left side, right? Because you drop more power on the right side, whereas you drop only less power on the low side. So, do you think you can exploit that fact when you design the high and the low duty ratios, or would that not be of any concern at all?
I have to think about it a little bit, but theoretically what we want to do is we want to ripple back and forth across the maximum power point. We want the maximum power point to occur over the ripple. Whether we could split that ripple up, maybe, but I don't know if it would be really worth it. Because when you actually start tracking the maximum power point, in the milliamp range, this is rather flat from some perspective. So, yeah. Catherine?
You move up to the window, move it leaving the buffer, going to the maximum power point. One more?
No. So which
like the time scale for going up to the maximum power point?
Oh,
is right there.
Yeah.
So it's in like a half, so like 0.3 seconds.
Mm-hmm.
This is mostly static, right? Is it under a light? Do you see the light?
This is the DC array under the bench upstairs.
The only thing I had a question about, so the window is following it too, right? So
correct.
What happens when we have really fast transients and it's a cloudy day and the sun's up and down, so everything's moving up and down. So your window has to follow your current. So is that a problem for you, or is it going to be just as fast as?
Well,
it's changing really quickly.
Yeah, you could argue that that's why this doesn't go nearly straight up, because when the current leaves the window, the microcontroller has to stop and reevaluate and shift its window up. So it's kind of iterative, and it just shifts up until it achieves a windowed measurement, and then it evaluates the DDR-CC.
So it doesn't have an error or anything. If it goes too fast,
it'll just reevaluate. Correct. Andrew.
When you say tracking efficiency of DDR-C versus P&O, are you using dithering on perturb and observe, or are you using the discrete value?
That's a really good point. I should put that in here. This is undithered. This is discrete values of duty ratio.
Okay.
And so
you're kind of getting both effects there, the tracking
correct.
And the dithering effect.
So the P&O dithered would be here, no question about it. But our update speed would be slower.
Right. So I guess the advantage would be if you were changing a lot, if you had a really cloudy day or something going across DDR-C, you might see a little bit of a difference.
Correct. Correct. Or mobile applications, or wearable PV cells.
Yeah.
PV cell headbands. So, is that it? Okay, Troy.
How does the window ADC improvement scale with ADCs that have higher, say, for an ADC that's is it linear? Or I guess just based off of all the math presented,
Yeah.
that an ADC with 12 bits, how would it improve a little bit?
I think that would go back to the quality of the ADC itself and the quality of the circuit layout. I think that's what would be more dependent on. Theoretically, I'm sure. Well, but you have to consider the relative value of the noise compared to the native resolution of the ADC. So if under these noise conditions, the noise minimum realistically achievable resolution may be the same with a 12-bit ADC as 10-bit ADC, depending on how that worked out. So I'd have to think about that a little bit more, but you could end up in the same place. I'm not totally sure. Andrew seems to be shaking his head, so that's probably a good sign of the National Instruments guy.
Or 10 or 12 or even 12 and 14 bit ADCs where they'll have the resolution there of 12 bit versus 14 bit. 12 bit will have 1 bit of noise and 14 bit will have 4 bits of noise. The noise will be the same. But if you can't find a better 12 bit that has a 1 bit noise, then you are going to see, I mean, there's 4 times less noise.
Or if you could oversample, obviously that helps, but we can't oversample here. So, well, thank you for your time.
Hello. Hello. Hello.
No.
Going to say anything?
No.
I can start. Right?
Our second speaker today is Shibin Qing. Shibin received his bachelor's degree in electrical engineering from Huazhong University of Science and Technology in 2012. He's currently a master's student at the University of Illinois with Professor Palawa, and his research interest is in power electronics and photovoltaic applications.
Thank you very much, Siming. So good afternoon. Today I'm going to talk about the work we have done on merging differential power processing with microinverter. And to my knowledge, this is actually the first dynamic demonstration of DPP control working together with a microinverter. And in this presentation, I'm going to introduce what is DPP and how it works, and how do we control it, and the implementation challenges we have met, and our solutions. And also, I'm going to show some experimental results that verify the effectiveness of this DPP approach. So to start with, in PV system, well, conventionally, modules are often connected in series and send power through a central inverter to the power grid. But series connected PV module has well-known mismatch problem due to various reasons. And the current mismatch exists between different modules and even between different submodules within one PV module like this. And this mismatch is especially severe in residential application where you have a more complicated environment. And to help solving this mismatch problem, people have developed microinverter, which interface each individual PV module and perform a module-level maximum power tracking. And it has become microinverter has become the dominant solution in residential application. But as I just said, the current configuration of microinverter does not compensate for mismatch between submodules within one PV module. And it can be especially severe in residential application. So here I'm just showing an example in which you have one PV module of 3 submodules, and each one is receiving different irradiance, and that's producing different power. So the power versus voltage characteristic look like this. They have their own characteristic, and they have their own optimal point. And to the macroinverter here, this PV module characteristic actually look like this line. So the macroinverter cannot extract the optimal power from each submodule, and it can actually be trapped. The maximum power tracking algorithm of the macroinverter can actually be trapped in the local maximum. I'm going to show an example later to illustrate this point. So how are we going to solve the mismatch problem between submodules? I think one obvious solution is that we can take macroinverter to submodule level, but to the best of my knowledge, no one has ever done that because the dollar per watt cost will be very prohibitive. So for cost reason, that's not a solution. And a more viable solution nowadays is DC optimizer, which I'm showing here. So basically, DC optimizer is inserted between each submodule and the entire string to ensure that DC optimizer can perform submodule level maximum power tracking. And here I'm showing an excellent example of submodule level DC optimizer. But the problem with DC optimizer is that each DC optimizer has to process the full power of each submodule. So it will be it will have a relatively high power rating requirement, and it will actually limit the DC optimizer will actually limit the system efficiency. And we'll show an example later. But the question is, can we overcome this limitation and do better? And the answer is yes. And this can be done by differential power processing. There are many different variations of DPP architecture that has been proposed, and you are encouraged to read the paper for more reference. But what I'm showing here is element-to-element structure, which we believe is the most feasible solution for microinverter. So here, each DPP converter is configured as a bidirectional buck-boost converter, and the bulk power that is common to all PV submodules actually goes to the microinverter directly without any intermediate conversion. And the DC to DC converter only processes the power mismatch, which is typically very small compared to the full power. And because of that, DPP is actually advantageous over DC optimizer in terms of efficiency, converter rating, and ease of integration. And here is an example to illustrate that point. So assume we have a PV module with 3 submodules, and each is receiving different irradiance and is generating different power. So there is a mismatch. So if we use DC optimizer solution, and we assume a 95% efficient DC optimizer, as you can see here, because each DC to DC converter is processing the full power. So even you only have 5% loss, the overall power loss penalty is still significant. But if we process the same power, the same irradiance condition with differential power processing, and because each converter is actually processing the differential power, which is relatively small. So even if we assume a much less efficient converter, which is 85% in this case, we are still getting like a much smaller power loss in the end. So as I mentioned before, for DPP system, the system efficiency is fundamentally limited by the DC to DC converter efficiency, which is exactly 95%. But for DPP system, these two efficiency are decoupled, and we can achieve higher efficiency even with less efficient converter. So that's a benefit. And of course, each converter can be rated at a much smaller power rating. And another point is that DPP is relatively easy to integrate into the existing PV module design, because to insert DC optimizer, you have to break the internal connection of a PV module and put the DC optimizer, which require a lot of work actually. But for DPP converter, you can simply attach them in parallel, which is shown here. So you don't really need to alternate any existing panel or microinverter design. So DPP is good, but excuse me. So DPP is good, but how does it work exactly, and how can we actually control it to exploit all the benefit it can offer? So here, the conventional, the commercial microinverter typically run a voltage reference perturb and observe algorithm, which means it will regulate the string voltage. And for DPP converters, they can adjust their own duty ratio to enforce a certain voltage ratio between neighboring converters. So the relation of voltage and duty ratio is actually shown here. So this DPP system is actually governed by these three equations. So for each insulation irradiance condition, each submodule has its own maximum power point voltage. Let's assume it's V1, V2, and V3 star. And this will translate to a unique combination of duty ratio and module voltage. And the goal of this DPP maximum power point tracking control is to find this unique combination. And how can we do that? So the power output of a module is simply the power voltage multiplied the power current, multiplied by the power current. And because, as we said, microinverter is actually regulating this voltage, and we can make the control loop for DPP converter very fast compared to the microinverter, such that for DPP converter, this VM can be viewed as temporarily fixed by the microinverter. Then the only task of DPP converter is to maximize the string current, which is the listed as the control objective here. And we can take a look at the timeline of this control. So once in a while, the microinverter will update the module voltage. And in between, DPP converter can operate really fast to maximize the string current. And if they work together properly, and the module power can actually be maximized. And for DPP converter specifically, for any fixed module voltage, we can visualize the module current as a function of the duty ratio here. So as you can see in this plot, so module current is a nice concave function of the duty ratio. So if we apply a simple perturb and observe method, or say like Q climbing method, it's guaranteed that we can find the optimal point. But the only remaining problem in this control method is that if you read this plot carefully, near the optimal point, the surface is actually very flat, which means for a certain duty ratio perturbation, the changing string current can be quite small. And it's going to be an implementation challenge for us to, how do we sense that small current change? And this is where I actually borrow some idea from Chris. We have a moving window technique that can help us sense small current change. So conventionally, when we want to measure current, we typically directly scale the current signal to fit it into the 3.3 volt or 2.5 volt ADC, which have a limited resolution. So in this case, because we are limited by the 0 amp to 5 amp current range coming out from the PV module, so if we scale it directly, 1 microamp change will only result in 0.7 millivolt. 1 milliamp change will result in 0.7 millivolt change in ADC input, and will only result in 0.82 effective ADC value, which is quite too small. Typically the change due to a duty ratio perturbation is about 20 milliamp, which will translate into only 16-bit ADC. And if you are familiar with microinverter ADC, so typically it's coupled with quite significant noise. So 16-bit ADC in 40,000 range is not enough. It's not large enough to determine the relative current change. So what we do is that we basically scale the current first, and we subtract moving bias to remove the large DC component from the current, and we only amplify the relatively small current change, because in perturb and observe method, we only care about the relative change. We don't really care about the absolute value. So for a more complete detail, you are encouraged to read the paper. But what we end up achieving is that after applying this technique, 20 milliamp change will actually result in 320 effective ADC value, which can be picked up easily by the microinverter ADC. And for a more complete analysis on this moving window technique, you are encouraged to listen to Chris' presentation, which is Tuesday session T34. And to summarize, the control procedure is that basically before each iteration, we adjust the voltage bias to center the current signal in the middle of ADC range. And we take the measurement, we perturb the duty ratio, and we measure the current again. And we only care about the relative change. And we decide the direction of duty ratio we want to go in next step. So it will look like this. It will start from a random initial point and climb to the optimal point. Here next is about how we implement this control algorithm. So basically what we have done is that we integrate 2 DPP converter and 1 microcontroller in one piece of PCB, and we use a relatively low-cost passive capacitor diode level shifting circuit to help reduce the cost and size. And here are just specification of this converter. And the highlight, the nice thing is that we do achieve a relatively small circuit footprint, which goes right into the microinverter junction box. So it will offer some benefit in terms of cost. I will just skip this. So this is our experimental setup. So we basically take a commercial off-the-shelf microinverter from SolarBridge, and we put AC power source to simulate the grid, because this microinverter won't operate unless we provide a grid reference. And we also use a PV emulator, which actually use the real PV hardware to preserve the real dynamic of each submodule. So for more details about this emulating technique, you can read this paper shown here. But this is basically our experimental setup. And here is the experimental result. So as I mentioned before, microinverter can actually be trapped in a local maximum, which is exactly happening here. So when we have mismatch between submodules, without BPP turning on, the microinverter perturb and observe algorithm actually stuck in this local maximum. And we are plotting the real-time power output from the microcontroller. So as you can see, once we turn on the DPP, it actually go up to the optimal point exactly. So DPP does help a microinverter to extract the optimal power from the system. So here is just showing here is for different situations, the evolution of duty ratio. So we start from a random initial point, and it quickly converges to the optimal value. For every 1 second, the microinverter will update its voltage reference. So here, approximately every 1 second, you can see there's a change in operating point of the DPP converter. So the timeline, the operation of these two control loop actually align well with each other. And I do want to mention that the update of microinverter is actually faster in practice than 1 second. And we are slowing down the microinverter just for data acquisition purpose. And the last point of the experimental result is that I want to show you the quantized benefit of this DPP approach. So for different irradiance condition, if we use microinverter without DPP, and these are the potential power loss due to the microinverter unable to track the optimal point. But once we turn on the DPP, we actually reduce the power loss, potential power loss, by about 20 times. So it does improve the benefit of merging DPP with microinverter. So here is my concluding remark. So DPP is a potential low-cost solution to compensate PV module mismatch between different submodules. And this is the first the working dynamic demonstration that DPP and microinverter can work together. And so for future work, even more efficiency improvement and cost reduction can actually be achieved by integrating DPP and the microinverter together. And at last, I do want to thank John and Chris and RPE for paying my tuition. And I'm happy to take any question you have now. Thank you. Okay, no question. Good. Message well received. Thank you.
You showed the chart that at the
Uh-huh.
I saw that you were compensating the compensation you still have this like little box you said had a little bit discussing that.
Well, sorry, what do you mean? Like, you mean this one? Yeah, indeed. Yeah, that's possible. Well, that one is because once like all this gate driver and everything won't turn on until you have 10 volt. So once it goes 10 volt, everything turn on and it's consuming a little bit power. So actually pull the power curve down. So I think it's not very likely because once you go to this low value, it will just turn off the DPP automatically. So you will have a smooth curve again.
So you're really getting the power that's going away. Like you're operating a little bit above that, but it's just going directly to the DPP. Is that correct?
Sorry, what do you mean?
So the dip is due to them turning on.
Uh-huh.
You have losses.
Yeah, I'm using a linear regulator to power the gate driver, so it's probably not very efficient. And it's well, it's right before the microinverter.
Are picking up the DPP power.
Yes. The DPP actually draw power from the panel.
I think to answer your question, I think there's actually not that dip on the PV. So there's no like the local maximum will get caught on the PV side, but that's coming out to the DPP.
Yeah, and
so
also
it's still, like the curve itself is still clear.
Yeah, it's not very likely you will operate at 10 volt range because I think in that case, microinverter will probably just turn off itself because it has some safety check before it turn on. So it's like that's actually introduced by DPP, and well, that's a very good point actually. Yeah, very sharp eye. Thank you. Okay, thank you very much.